we have seen the properties of Jacobians. One of the properties that we saw was if u is equal to f of x, y and v is equal to g of x comma y. That means we have functions u and v which are functions of x and y. In that case, now uv with respect to x comma y times dou x comma y with respect to u comma v. Now here u and v are functions of x and y, and x and y are functions of u and v. Yes, so here you have x equal to p of u and y is equal to q of v. Now if we evaluate this, we will get 1. So basically what does this mean? Whenever you multiply two numbers and you get 1 and they depend on each other and they are basically say if this is 4, then you can actually see that this is nothing but 1 by 4 equal to 1. So that means that one of them is an inverse of the other. Yes, so if you have a Jacobian, then let's say this is Jacobian and this is Jacobian dash, right? So this is equal to 1. Now this is very, very important to remember. So if you are asked to find the inverse, you have to evaluate this. Okay, so let's do some problems. Now let's say x is equal to r cos theta and y is equal to r sin theta. Find j and j prime, Jacobian and its inverse. Dou x by dou r is equal to what? Cos theta. Dou x by dou theta is equal to minus r sin theta. Dou y by dou r is sin theta. Dou y by dou theta is equal to r cos theta. Okay, now let's find the Jacobian. Is equal to cos theta minus r sin theta and r cos theta. R cos square theta minus into minus plus r sin square theta. So r is the Jacobian. Now we have to find the inverse of that. Okay, we can directly say 1 by r, but let's see whether that really is the case or not. So let's find r comma theta with respect to x comma y. So in this case, what will happen? We have to find dou r by dou x, dou r by dou y, dou theta by dou x, dou theta by dou y. Now we have to figure out dou r by dou x. That means r with respect to x. So r is equal to x equal to r cos theta. So remember here you have to remember what has happened much before. We know x square plus y square is equal to r square. Y is equal to r sin theta. We also know tan theta is equal to y by x, which means that theta is equal to tan inverse of y by x. Okay, so now we can find the inverse of the Jacobian. Let's differentiate with r with respect to x. So we get 2x equal to 2r dou r by dou x. So which is dou r by dou x equal to 2x by 2r, which is equal to x by r. With respect to y, again 2y is equal to 2r dou r by dou y. So dou r by dou y is equal to 2y by 2r, which is y by r. Now let's differentiate theta with respect to x and y. So dou theta by dou x is equal to 1 by 1 plus y square by x square times minus y by x square. So if we simplify this LCM, so this becomes x square, 1 becomes x square in the denominator can go on top. So x square by x square plus y square times minus y by x square. This gets cancelled and we are left with minus y by x square plus y square. Now dou theta by dou y. Dou theta by dou y would be x square by x square plus y square 1 by x. So this and this gets cancelled and we are left with x by x square plus y square. Now remember, x square plus y square is equal to r square. So minus y by r square, x by r square. Okay. So now let's bring in the let's calculate the determinant. So j prime is equal to x by r, y by r minus y by r square, x by r square. So x by r times x by r square plus y by r times minus, no, not minus, y by r square. So x square by r cube plus y square by r cube, which is x square plus y square by r cube, which is equal to, remember, x square plus y square is r square. So r square by r cube, which is 1 by r. So that is, so here the critical part is that you have to differentiate correctly. Okay, let's do the next problem. Let's say x is equal to u times 1 minus v and y is equal to uv. Find or okay, find j and j prime. By the way, how do you know that what you have done is correct? You just have to check whether j times j prime is equal to 1. J is r here times 1 by r equal to 1. Okay, same thing we have to do here as well. So dou x by dou u is equal to 1 minus v. Dou x by dou v is equal to minus u. Okay. Dou y by dou u is equal to v. Dou y by dou v is equal to, so the Jacobian would be 1 minus v minus u, v u, 1 minus v minus into minus plus uv, which is u minus uv plus uv. These two gets cancelled and we are left with x equal to u 1 minus v, u minus uv, u minus y. Okay, so u is equal to x plus y. Now let's look at y is equal to uv. So y is equal to, u is nothing but x plus y. We have seen that now. So v is equal to y by x plus y, which can be written as y into x plus y inverse minus 1. Okay, now let's find the partial derivatives. So dou u by dou x is equal to 1. Dou u by dou y is equal to 1. Dou v by dou x is equal to minus y divided by x plus y square. Dou v by dou y is equal to x plus y times 1 minus y divided by x plus y the whole square, which is equal to x plus y minus y by x plus y the whole square, which is x by x plus y square. So now let's evaluate the Jacobian for this. So dou u comma v with respect to x comma y, which is okay. Let's find the determinant. Dou u by dou x is 1. Dou u by dou y is 1. Then this is dou v by dou x minus y by x plus y the whole square, x by x plus y the whole square, which is equal to x by x plus y the whole square plus y by x plus y the whole square, which is x plus y divided by x plus y the whole square. This and this gets cancelled, so we are left with 1 by x plus y. Now 1 by x plus y is equal to nothing but u, so it is 1 by u. Now j was u, j prime is 1 by u, so which is equal to 1. So that verifies it. Okay, let's see. Now we are given functions u is equal to x minus y plus 2z, v is equal to xy minus 2yz plus 3zx, w is equal to x square plus y square plus 4z square plus 10xz minus 8yz. Now what we have to show is that these functions are functionally dependent, and we have to find the relation between these dependent functions. So we have to find the relation as well. Let's find the Jacobian. Now Jacobian would be dou u v w with respect to x, y and z. Okay, dou u by dou x 1, dou u by dou y would be minus 1, dou u by dou z would be 2. Okay, let's make some space so that minus 1, 2. Now dou v by dou x would be y plus 3z. Now dou v by dou y would be x minus 2z, and dou v by dou would be minus 2y plus 3x. Dou w by dou x would be 2x plus 10z. Dou w by dou y 2y minus 8z, and finally dou w by dou z would be 8z plus 10x minus 8y. Okay. Now let's do some column and row manipulations. Column manipulations. So let's say C2 plus C1. If we do, then this will become 0. 1y plus 3z, 2x plus 10z. This becomes a 0. We basically add, so x plus y, 3z minus 2z is z. This becomes 2x plus 2y plus 2z. Okay, so one of the operations that we have done is C2 plus C1. Now let's make this 2 also as 0. So for that, what we have to do? C3 minus 2C1. So this will become 0. Now remember, we have to multiply C1 by 2. So this will become 3x minus 4y minus 6z. This will become 6x minus 8y minus 12z. Now in the second column, x plus y plus z is common. And this is 2 times of that. So x plus y plus z, we can take it out. Similarly, here also 3x minus 4y minus 6z is common. This is twice this. So 3x minus 4y minus 6z. And now if we write the determinant, y plus 3z, 2x plus 10z, 0, 1. And this becomes 2. This is 1 and this becomes 2. Now we don't have to do any calculations as such, because if 2 columns are equal, then the determinant is 0. And 0 multiplied by these 2 is also 0. Now if j is equal to 0, implies that u, v, w are functionally dependent. This should be R. Now we have to figure out the relation between these functions. Let's copy these equations again. Now let's see. If you notice, here you have x square, here we have x square, y square, z square, right? So we can get this only if we square the u. So let's begin with u square. So u square would be what? X minus y plus 2z, x minus y plus 2z, x minus y plus 2z, x square minus xy plus 2xz minus xy plus y square minus 2yz plus 2xz minus 2yz plus 4z square. Okay, let's simplify this. X square, let's bring the square terms together. 4z square minus 2xy, so 2xy gone, xz. Okay, so plus 4xz yz. Where is yz? Okay, minus 4yz. Okay, so we have got this. U square is equal to. Now let's see whether we can write w and v in such a way that we get this expression. So that way we relate these 3. So we have w, and from w we have to get this using v. So xy, v is xy. In w we don't have xy, w and v, and we have to find some relation between these two to get this part. So w is x square plus y square. V doesn't have x square plus y square. So we need it in this. So if we add these two, we still get x square plus y square. Even if we subtract, we get both x square plus y square. So that's not a problem. Now what we need is 4z square. Again, that is not a problem. So we just have to focus on xz and yz. So xz, how do we get xz? Here it is 4, there it is minus 2. No, 3. There it is 3, here it is 4. We have to get 4. So xz, xz. So 3 to 6, 10 minus 6 is 4. Let's see whether we get that. W minus 2v is equal to. So W is x square plus y square plus 4z square plus 10xz minus 8yz minus 2v. 2v is 2xy minus 4yz plus 6zx or xz. X square plus y square plus 4z square plus 10xz minus 8yz minus 2xy plus 4yz minus 6xz. X square plus y square plus 4z square. This and this. So we get plus 4xz minus yz. So minus 4yz, and we are left with minus 2xy. So where does this go? Minus 2xy. So if you notice, this and this are equal. So u square is equal to w minus 2v. Now u square plus 2v minus w equal to 0. So this is the relation between these three equations or functions. Of course, if the Jacobian is not 0, then no problem at all. They are not functionally dependent. Okay, so I think that's enough for today. Bye for now.